Wall display box, front acrylic plus first timber blocks. Alright, in this video I'm going to show you the CAD workflow for the start of our wall display box. First, I'll show you the completed model so you understand where we're heading. Then I'll roll back to the start and rebuild the first steps. The 3mm acrylic front panel and the first timber blocks that the acrylic sits inside. Part 1. Open the completed model. Quick overview. I'm going to open Owned by Me and click Wall Display Box. Now I'm going to jump to the first features in the feature list, starting with Sketch 1 and the first extrude. I'm going to right-click and select Roll to Here. That rewinds the model so we can rebuild it from that point. Part 2. Create a new part studio so you can follow along. Now I'm going to create a fresh part studio to model the acrylic panel. Down the bottom left, I'll click the plus button and choose Create Part Studio. I'm doing this just to demonstrate the workflow cleanly. You should create your own part studio in your own document and follow along. Part 3. Sketch the acrylic front panel, 293 by 416. Now I'll click Sketch. I'm going to choose Center Point Rectangle. It's important to click in the center, especially when we're working with parts that might become asymmetrical later. Centering gives us lines of symmetry that are useful for mirroring and aligning features. So I click the center point and drag out a rectangle. Now I'll dimension it. This panel is 293 by 416. I'll click the first dimension and type 293, then press Enter. Then I'll click the other dimension and type 416, then press Enter. Cool, that's the acrylic face. Part 4. Extrude the acrylic to 3mm. Now I click Extrude. Extrude means we're turning that sketch into a 3D part. Our acrylic is 3mm, so I'll type 3 for the thickness. Before I confirm, I'm just checking that the extrude is set to New. New means this becomes its own part. Now I press OK. That is our front acrylic panel. Part 5. Sketch the rebate zone where acrylic sits. Next, we're going to start modeling the timber blocks that the acrylic sits inside. I'm going to click the front face of the acrylic, then click Sketch again. Now I'm going to draw the inside offset where the acrylic will locate into the timber. Press D for dimension. The first offset is 6mm. This represents the setback or rebate area where the acrylic sits in from the timber edge. So I'll create an offset rectangle and dimension that offset to 6mm. Now I'm going to define the timber block width around the edge. This next dimension is 10mm, so I'll sketch the next rectangle/boundary and dimension it to 10mm. At this point, we've got sketch geometry that represents the acrylic location and the timber block area. Part 6. Extrude the first timber blocks as new parts, top plus bottom. Now I click Extrude. Important, I'm not extruding the whole face. I'm selecting only the regions that represent the top and bottom blocks. Now for the depth, the timber block total depth is 100mm. We're going to build it using two key values, 10mm in one direction and 90mm in the other direction, so the total depth ends up at 100. Before I press OK, this is critical. I must set the extrude to new. If it's not on new, you won't create new parts. you'll accidentally merge into the acrylic. So I switch to new. You should see the part color change. That's how you know it's a separate part. Now I set the extrusion depth. First direction is 10 millimeters. Then I'll flip the direction, use the second direction, and set that to 90 millimeters. Now press OK. Great, now we have the first blocks. Part 7, repeat the extrude for the matching blocks. Same sketch, new parts. Now I'm going to repeat the same process for the matching blocks on the opposite side. If needed, I'll unhide the sketch so I can select the same profiles again. Again, click Extrude. Select the correct regions. Set it to New. Extrude 10 millimeters one way and 90 millimeters the other way. Press OK. Now we can see the acrylic panel and the timber blocks as separate parts. Quick checkpoint, pause here. Pause the video and confirm you have. One acrylic part, 293 by 416 by 3 millimeters, and timber block parts created as new parts, different color, extruded to a total of 100 millimeters depth. Alright, next I'm going to add the backplate parts by repeating this existing part using a feature called Linear Pattern. First, I'm going to click Linear Pattern. Now, under Entities to Pattern, I'm selecting Part 1, the part I want to copy. Next, for the direction, I'm going to click an edge or a corner of the part to set the direction arrow. Now I'll set the distance to 75 millimeters. You'll see the preview pop up straight away. The copied part appears in position before I even press OK. That's how you know the direction and spacing are correct. If your copy goes the wrong way, just click Reverse Direction or reselect the direction edge. Once it looks right, I press OK. And now that backplate part is duplicated and placed exactly where we need it. Alright, now we're going to check what we've built using Section View. And then we'll adjust the rebate so the acrylic has a proper clearance fit. First, I'm going to click on the right plane. Then I right-click the right plane and choose Section View. Now, notice what you can see in Section. There are areas where parts visually overlap in red. That's normal at this stage. We haven't added clearance yet, so we're about to fix it. Next, I'm going to check the rebate tolerance from the front. I'm going to click the front face of the acrylic, then press N for normal so we're looking straight on. Now I click Sketch on that face. I'm going to choose Center Point Rectangle again. Important tip: when you place this rectangle, you don't want it snapping onto random points or those little pop-up constraints. So I'm going to hold Shift while I place it. That helps avoid snapping. Now I press D for dimension. The original rebate offset was 6 millimeters. For a better fit, we're going to give the acrylic a small clearance. So I'm setting this to 6.5 millimeters. That gives us 0.5 millimeters clearance on each side. Enough room so the acrylic isn't jammed tight, but it still sits neatly. Now I'm going to cut that clearance into the timber. I click Extrude, and this time I switch it to Remove. Now, really important, we do not want to remove from everything. If we leave it on Merge with All, it can affect parts we don't want to touch. So I'm going to use Merge Scope, and I'm only selecting the timber frame parts as the parts to remove from. Now, for the depth, I'm going to aim for about 4 millimeters. In the video, you might see me adjust this visually, but the target is a rebate depth around 4 millimeters, so the acrylic sits nicely. Once that looks right, I press OK. Now I'll use Section View again to confirm the result. You should be able to see a clean rebate with clearance, and the acrylic has room to sit without clashing. If you can't select a part easily while Section View is on, you've got two options. Either turn Section View off temporarily, or select parts directly from the parts list at the bottom. Back rebate pocket for 3 millimeter. Acrylic plus Cleat plus lock, center rectangle plus remove plus merge scope. Alright, we're just going to start by looking at the finished product so you can see what we're aiming for. Notice there's a rebate pocket on the back where the back acrylic sits inside the timber frame. The back acrylic is 3 millimeters thick, and we're allowing 2 millimeters clearance per side. So there's about 4 millimeters of wiggle room overall, so it can slide in nicely. Now, the plywood is 16 millimeters thick, so the rebate comes in 8 millimeters, basically halfway through the plywood. That gives a strong border around the perimeter, and it also creates space for the cleat and the 3D printed locking mechanism. The key numbers for this back pocket are 8 millimeter border thickness around the perimeter, and a 15 millimeter pocket depth from the back face. That's deep enough for the cleat and lock, while keeping strength around the edges. Now let's go back to the model we're working on together. First, make sure you're looking at the back orientation. Check the view cube in the top right so it says back. I'm going to click on one of the back timber faces and I'll start a sketch. I'll choose center point rectangle. Click in the center, and when you place it, hold Shift so it doesn't snap to random points or pop-up dimensions. Now I'll dimension the rectangle using gaps from the edges. Press D for dimension. We want an 8 millimeter border, so I'm setting the gap from the edges to 8 millimeters. And I'll repeat that so the border is consistent around the whole pocket. Press OK to finish the sketch. Now we cut the pocket. Click Extrude and switch to Remove. Select the sketch region that represents the pocket. Now, this is the important part. Set the depth to 15 millimeters. Make sure you set the depth before you confirm. Next, go to Merge Scope. We only want to cut into the timber frame pieces, not the acrylic. In my model, the timber frame parts are parts 2 to 4, so I'm selecting parts 2 to 4 as the merge scope. A quick tip here, I usually hide the acrylic parts before this step, just to prevent accidental selection. But it's optional if you're careful. Now, if you get an error like Merge Scope Invalid, it's usually because the selection order is wrong, so here's the fix. First, make sure your Merge Scope parts are selected. Parts 2 to 4, then make sure your Remove region is selected, the pocket face, and confirm that the acrylic is not included in the Merge Scope. Once that looks right, press OK. Now you should have a clean back rebate pocket, 8 millimeters of border thickness, and a second rebate for 3D printed lock, offset plane plus offset sketch plus remove. Alright, if we look at the finished model, you'll notice there's a second rebate on the inside of the frame. This rebate is specifically for the 3D printed locking part to sit into. The reason we do it this way is consistency. It matches the same 6.5 millimeter rebate width that we use on the front, so it's standardized and easy to manufacture. Now, back to the part studio we're working on. Step 1. Create a plane, 8 millimeters in from the inner wall. First, I'm going to select the vertical inner wall of the timber frame, the surface that forms the inside edge of the box. Important, we are not starting a sketch directly on that wall. Instead, we're going to create a new plane. I go to Plane, then Offset Plane. For the offset distance, I type 8 millimeters. Now check the arrow direction. We want the plane to offset inwards, so it sits inside the frame where the lock will live. Press OK. Now we've created a new plane. It'll show up as Plane 1. Step 2. Sketch on the new plane and offset the perimeter by 6.5 millimeters. Now I click Sketch on Plane 1. For this part, we're going to use the Offset tool. You can click Offset or press O on the keyboard. Now, we're going to select the inner perimeter edges of the front face opening, basically the inner boundary we want to reference. Once those edges are selected, I set the offset value to 6.5 millimeters. Make sure the offset goes the correct way so it creates a clean channel shape. You should now see a nice consistent outline that represents the rebate pocket for the lock part. Finish the sketch. Step 3 is Extrude. Remove the lock rebate pocket, 4 millimeters. Now I click Extrude. Switch it to Remove. Select the sketch region that represents the rebate pocket. For the remove depth, set it to 4 millimeters. In this step, it's safe to use Merge with All because only the timber frame parts intersect. We're not cutting acrylic here. Press OK. Step 4. Check it with Section View. Now let's verify it worked. Right-click the right plane and turn on Section View. Then press N for normal and inspect the cavity. You should see a clean, consistent rebate pocket for the 3D printed lock, and it should look standardized, matching the rebate style we've used elsewhere. Sketch the upper 3D printed Cleat profile, Onshape. Alright, next we're going to sketch the profile for the 3D printed Cleat. This is the upper cleat that will mount to the box, and it will slide onto a matching lower cleat that's fixed to the wall. Before we start, I'm going to show you the finished model so you can see what we're aiming for. You'll notice the cleat creates a second rebate style feature, and the geometry is kept consistent, so it's easy to manufacture and easy to assemble. Now I'm going back to the part studio we're working on, the one with the timber and acrylic. Step 1. Section view setup. I'm going to use the right plane so we can draw this accurately in section. Click the right plane, press N for normal, and turn section view on. Now we're seeing a clean cut through the box, perfect for tracing the cleat profile. Step 2. Start a sketch and rough in the cleat shape. Now I add a new sketch on the right plane. I'm going to draw a rough cleat profile first, then we'll add proper dimensions afterwards. So I'll sketch the main shape from memory. It comes down, then it slopes on the 45-degree face, and then it returns back to the base. If you overdraw lines, that's fine. We'll trim it. Now I'll use the trim tool, the scissors, to clean up any extra sketch lines and close the profile. Step 3. Add key dimensions. Accuracy comes from dimensions, not eyeballing. Now we lock it in with dimensions. First, the main angle. This face is 45 degrees. Next, the vertical drop. This is 10 millimeters. Now the cleat thickness. The profile thickness is 8 millimeters. And now we add clearance. Because this is a printed-to-printed cleat, and we want a looser fit to allow for small inaccuracies, I'm adding 0.2 millimeters clearance. In this example, I'm applying that clearance around the edges of the profile so the cleat doesn't bind during assembly. If your cleat ever feels too loose or too tight later, a better approach is to apply clearance only on the sliding faces. But for now, we'll keep it simple and consistent at 0.2. Extrude upper cleat plus add M5. Counterbore holes, 3 holes. Alright, next, we're going to turn this cleat sketch into a 3D part, and then we'll add the screw holes so the upper cleat can attach to the timber frame. Step 1. Extrude the cleat as a new part. First, I'm going to turn off section view. Now I'll click extrude. Make sure the extrude is set to new because this needs to be its own 3D printed part, not merged into the timber. I'm going to extrude it symmetric, so the total length is 100 millimeters. That's 50 millimeters each way. Press OK. Now I'll hide the back acrylic part so we can see inside the box clearly. Step 2. Section view so we can place holes accurately. Now I'll turn section view back on using the top face so we can see inside the box. This makes it much easier to place holes in the correct position without guessing. Step 3. Sketch hole locations, construction line plus dimensions. Now I'm going to create a new sketch on the top face of the cleat. First I'll draw a line across as a construction line. This will control where the centers of the holes sit. Now I'll press D for dimension. The hole line needs to be 4 millimeters from the rebate reference, which works out to 19 millimeters from the back edge in this model. So I'll dimension that construction line into position. Now I'll place 3 hole points along that line. Hole 1 is 20 millimeters from the left edge. Hole 2 is 20 millimeters from the right edge. And the third hole comes in 8 millimeters from the inside edge. Press OK to finish the sketch. Step 4. Use the hole feature, metric counterbore M5. Now we're going to use the hole tool. Before we select anything, make sure we're on metric counterbore. Now I'll select the 3 sketch points, the hole locations we just placed. For the hole type, choose drilled and set the drill size to 5 millimeters. That's correct for an M5 cap screw. Set start from to start from part. Set the termination to blind. Now we copy the counterbore dimensions from the exemplar. 7.14 millimeters, 4 millimeters, 16 millimeters. Once those values are in, press OK. Quick warning, if you forget to click counterbore, you'll only drill a straight hole, and you won't get the recess for the screw head. So always double-check you're on metric counterbore before confirming. Cut acrylic slot plus chamfer plus small fillet. Alright, next we're going to cut out the slot in the acrylic so it clears the 3D printed cleat. If I turn on section view for a second, you'll notice there's a clash. The acrylic and the printed cleat want to occupy the same space. So this step is a simple fix. We're creating a clearance slot in the acrylic. Step 1. Sketch the slot on the acrylic first. I'll turn section view off. Now I'm going to click the acrylic face that needs the slot and start a sketch on that face. I'll choose center point rectangle. I want to start from the center, but be careful here. Don't accidentally snap to random sketch points or pop-up constraints. If you need to, zoom in and place it cleanly. Now I'm going to align the slot to the top edge of the acrylic. I click the top line of my rectangle, then click the top edge of the acrylic, and press I for coincident. That locks the top of the slot perfectly in line with the acrylic's top edge. Now I'll add dimensions. The slot width is 14.5 millimeters. Then we add clearance so it doesn't bind. I press D for dimension and set the clearance to 0.2 millimeters per side. That gives the acrylic enough room to slide past the printed cleat without scraping. Press OK to finish the sketch. Step 2. Extrude remove, acrylic only. Now I click extrude and switch it to remove. Important. We are only cutting the acrylic, not the printed cleat. So for merge scope, I'm selecting only the acrylic part. For the end condition, I'll just use through all. Because we're only removing from the acrylic, it's the cleanest and safest option. Press OK. Now if you look inside, you can see that slot has opened up and the clash is gone. Step 3. Chamfer the exposed edges, no knife edge. Next, we'll make this nicer to use by removing sharp edges. I'm going to apply a 2 mm chamfer, but only on exposed edges. Rule for students. Only chamfer edges you can touch. Do not chamfer edges that contact the timber or another part. If it touches another part, leave it alone. Otherwise, you change the fit. So I click chamfer, set it to 2 mm, and select all the exposed edges around the slot area that guide the acrylic in. Press OK. Step 4. Tiny fillet to kill the knife edge. Finally, I'm going to add a small radius to remove the last sharp edge. I click fillet, set the radius to 0.3 mm, and apply it to the knife edge. The edge that would otherwise feel sharp when the acrylic slides into the cleat. Press OK. That's it. The acrylic now has clearance, smooth lead-in chamfers, and no sharp edges. So it slides nicely without catching. Acrylic lock holes, U15, plus shaft extrude, plus start latch. Sketch. Alright, now we're going to put the holes in the acrylic for the 3D printed locking mechanism. Step 1. Sketch the holes in the acrylic. I'm going to click the front acrylic face and start a sketch. If you've already got an old hole sketch, delete it. We want this clean. Now I'll draw a circle for the first hole and dimension it. The acrylic hole is 15 millimeters diameter. So, U15. Now I'll locate the center of that hole, 20 millimeters from the side edge and 20 millimeters up from the bottom edge. Make sure you're measuring to the center point of the circle. Now I'll repeat the same thing on the other side. Another U15 circle, again 20 from the side, 20 up from the bottom. Press OK. Step 2. Extrude remove through the acrylic only now. I click extrude, switch to remove, and select both circular regions. Set the end condition to through all. And for safety, set merge scope to the acrylic part only. We do not want this cut affecting timber or printed parts. Press OK. Now the acrylic has clean holes for the locking mechanism. Step 3. Model the left-hand shaft only new part. We're only modeling the left-hand locking mechanism in this example. So I'll extrude the left hole profile again, but this time as a new part. Now watch the directions. From the outside face of the acrylic, I extrude 1 millimeter towards the outside and 11.1 millimeters towards the inside. That places the shaft correctly through the acrylic. Press. OK. Step 4. Start sketching the latch profile. Reference geometry. Now I'm going to hide the acrylic so we can see clearly, and I'll sketch on the circular face. This is where the latch geometry starts. Quick note. In the exemplar, you'll see an 18mm circle. That's not the acrylic hole. That's the diameter of the inner yellow cap on the printed part. You'll also see U30. That's just a reference circle to help shape the latch. Now I sketch the flat engagement feature. The slot thickness here is 6mm. That's the part that mates with the key shape. Next, I add the center key feature. That square is 8 by 8mm. Then I rough in the outer latch outline, referencing U35 for the overall handle profile.
Alright, now we're going to model the bottom cleat plate. If you look at the reference, it's basically a square in the center, with a chamfer on each end. The important part here is this: we want it parametric. So if the top plate width changes, this bottom plate updates automatically. That's the goal. First, I'm going to click on the face of the original orange top plate, then click Sketch. I'm choosing center point rectangle. Snap to the center point, but don't snap anywhere else. If you need to, zoom in, place it cleanly. Now I'm going to constrain this sketch so it matches the width of the top plate. I'll click this line, then click this reference point, and press I for coincident. Now watch this. These lines are dynamic. If I change the top width later, say to 150, this updates too. That's what we want. Next, we're building the chamfers into the sketch. Press L for line. Now press D for dimension. The bottom flat of the chamfer is 10 millimeters, and we do the same on the other side, 10 millimeters. Now the distance from the top of the chamfer to the top edge is 20 millimeters. This side is 20, and this side is also 20. You'll notice some of the sketch is still blue. That means it's not fully constrained yet. That's because we haven't locked in the chamfer angle. Set the chamfer angle to 45 degrees, and you'll see it turn black once it's fully defined. Now use trim and cut away the corner waste so the chamfer shape is clean. Cool, now we're ready to extrude. Click Extrude and make sure it's set to New Part. For the depth, don't guess a number. Set it to Up to Face and select the face it should stop at. If you can't select it easily, unhide parts, rotate the model, and pick the correct stopping face. If the wrong parts are getting in the way, just clean up your view. Unhide what you need, then hide what blocks selection, usually the front or back plate. Then double-check. New part, Up to Face, correct face selected. Press OK. Nice. That gives us the bottom cleat body. It's parametric, it matches the top plate width, and the chamfers are built in correctly. Next, we'll do the clearance cut, and then the mounting holes. Rest of bottom cleat. Clearance cut plus holes plus finish plus checks. Alright, now that the bottom cleat body is modeled, we're going to do 3 things. 1. Remove the clash. 2. Add the screw holes. 3. Soften the edges where it matters. Section A. Remove the clash. Triangle cutout. If I turn on a section view, you'll notice there's a clash between the top plate and the bottom cleat. That clash is normal at this stage, we just haven't cut the clearance yet. I'm going to use the right plane for this because it's the easiest way to see what's actually intersecting. Right-click the right plane. Section view. Then press N for normal. Quick tip, in section view, some edges look like they're missing. That's normal, you're looking at a cut-through. Now I'll start a sketch on the right plane, and I'm going to draw a simple triangle clearance shape. This triangle is basically carving out the space we need so the parts don't fight each other. Now I'll click Extrude, switch it to Remove, and I'll make it symmetric so it cuts evenly through the part. This is the point where it's easy to cut the wrong part. Make sure the cut is removing from the bottom cleat, not the top plate. If you're not sure, hide the top plate for a second, do the cut, then unhide. Press OK. Nice, clash gone. Section B. Add the wall mounting holes, countersink. Next, we need the mounting holes because this bottom cleat is what actually fixes to the wall. The goal is simple. The screw heads sit flush, nothing sticks out, and it mounts cleanly. I'm going to use the hole tool for this. Set it to metric and choose countersink. Now select the sketch points. Important, set your merge scope to the bottom cleat only. That stops the hole tool from accidentally drilling through other parts. For the hole settings, hole type is drilled. Drill size is 5 mm. And termination is through all. Through all is best here because it's future-proof. If thickness changes later, the hole still works. Now set the countersink values. Use 3.8 mm and 10.5 mm with a 90-degree countersink. Press OK. That gives us clean mounting holes ready for an M5 style screw. And because it's countersunk, the screw head won't interfere with the box sitting flat. Section C. Chamfers and fillets. Rule: keep wall faces flat. Now we'll soften edges, but only where it makes sense. Here's the rule. If a face touches the wall, keep it flat. Only chamfer or fillet edges that don't touch the wall. I'll add a small chamfer where fingers might touch, and a fillet where sharp edges could catch. You don't need massive fillets. Even a small radius makes the part feel more professional, and it reduces stress points in a 3D print. Press OK. Section D. Quick check. Does it still sit flush and does it clear? Before we move on, quick quality check. Turn section view on and off and confirm two things. 1. There's no clash. 2. Nothing we've added stops the part sitting flat to the wall. If it doesn't sit flat, it's usually because you chamfered a wall contact edge by accident. Just roll back, fix the selection, and carry on. Section E. Useful 3D printing filler. Quick printing tip while we're here. For cleats like this, print strength depends heavily on orientation. If you print it so the layer lines run across the thin sections, it can snap. If you rotate it so the layers support the load path, it usually lasts longer. And if the fit is tight in real life, don't redesign straight away. Try a tiny chamfer or sand the contact surface first. Section F. Evidence reminder. And remember, this is where your grade lives. Not just in the model, but in your proof. Screenshot the sketch with the key dimensions. Screenshot the hole settings. And write one sentence on why you chose that approach. Because in this standard, no evidence, no grade.